Hey everyone, and welcome. So, we're constantly hearing about these incredibly powerful new AI models, right? But here's the thing, a model all by itself is kind of like an engine without a car. It's got all this power, but you can't really go anywhere with it. So, today, we're going to build the car. We are going to look at the entire system, the full stack, that actually turns a powerful model into a tool that can solve real world problems. So let's just start with that big question right there. You get your hands on some amazing, top-of-the-line AI model, but is that really enough? And while that model is absolutely a critical piece of the puzzle, it's still just one piece. To make it truly useful, you've got to build a whole system around it. And to make this all feel a bit more real, we're going to imagine we're building a specific tool as we go through this. Okay, so here's our mission. We need to create an AI application that helps drug discovery researchers, scientists, understand and analyze the very latest scientific papers in their field. The stakes are super high, and the tech has to be just right. So, here's our roadmap. This is how we're going to build this thing, layer by layer. We'll start at the bottom with the foundational hardware and the models themselves. Then we'll figure out how to give it the most current data to work with. After that, we'll teach it how to handle complex tasks, and then finally, we'll design the actual application that our researchers will use every day. Okay, first things first, let's just zoom out and establish the big picture. Like we said, a great AI model is our engine, for sure. But an engine needs a chassis, it needs wheels, a steering wheel, the whole thing. To solve a real problem, we have to build the entire stack around it. All right, let's start at the very bottom of our stack with the two most fundamental layers. This is the foundation of everything we're building. The physical hardware that provides all the power, and the AI model that's going to provide the intelligence, the brains of the operation. First up, infrastructure. These huge large language models, or LLMs, they can't just run on any old laptop you have lying around. No way. They are incredibly power-hungry, computationally intensive, and they almost always need specialized hardware, specifically graphics processing units, or GPUs, just to run efficiently. And you've basically got three main choices for where this hardware actually lives. You could go on-premise, which means your company buys and manages its own super powerful servers. Or you could use the cloud, just renting what you need from a provider and scaling up or down whenever you want. And, for some of the smaller models, you might even be able to run it locally on a really high-end laptop. All right, next up is the model itself, the brain. And the first big decision you have to make is whether to use an open source model or a proprietary one. Open source models, they give you a ton of transparency and you can customize them, but they definitely require more work to manage. Proprietary models, on the other hand, are often way easier to get up and running, but they might come with usage costs and, you get a little less flexibility. And size really, really matters here. A large language model, an LLM, has this broad, general-purpose reasoning ability. It can kind of think about anything, but it costs a lot more to run. A small language model, or SLM, is much more lightweight and can be specialized for very specific tasks, like just summarizing text, and it can often run on way less powerful hardware. Now, just to give you an idea of the sheer scale of choice here, it's staggering. Model catalogs, like Hugging Face, list over 2 million different models. I mean, think about that. There is a specialized tool for pretty much any job you can possibly imagine. The real trick is picking the right one. Okay, so we've got our hardware and we've picked our model, but there's a huge problem, a really big one. Most of these models have what's called a knowledge cutoff date. Their entire understanding of the world is basically frozen in time, which for our research tool is a complete deal breaker. So this is the crucial point, right? Our tool for scientists is supposed to analyze the latest papers. But if the model was trained a year ago, it knows absolutely nothing about research published in the last 3 months. It is essentially useless for the main thing we built it to do. The solution to this problem is a really cool technique called Retrieval Augmented Generation, or just RAG for short. At its core, this is just the process of feeding the AI system new, up-to-date information from outside sources. It supplements the knowledge it was originally trained on. We're basically giving it a library card to a library that's updated every single day. And the process works in 3 key steps. First, we ingest the new data. So in our case, we'd be gathering up all those recent scientific papers. Second, we vectorize it, which is a fancy way of saying we turn all that text into numbers and store them in a special kind of database. And finally, when a user asks a question, the system retrieves the relevant new information to augment or beef up its answer. Pretty clever, right?
So, our model is now smart and it's up to date. Awesome. But what happens when a user asks a really complex question? Something that requires more than just a single simple answer. Well, that's where the orchestration layer comes in. You can think of it as the project manager for the AI.
Orchestration is all about breaking down a big, complex request from a user into a series of smaller, more manageable tasks. So instead of just spitting out one single answer, the AI actually uses its reasoning ability to create a multi-step plan to truly solve the user's problem. And this process is incredibly sophisticated. It starts with thinking, where the model actually plans out its approach. Then comes execution, where it might call on other tools, like a calculator or a web search, to go gather more info. And finally, and this part is just amazing, it enters a reviewing phase, where the model can literally critique its own first draft and then go back and improve it. We've built the engine, we've given it fresh knowledge, and we've taught it how to plan. Now it's time for the final, top layer of our stack, the application itself. This is where all that tech meets the human. It is all about the user experience. Now, this application layer has two key parts. The interface is what the user actually sees and touches, and it should be way more than just a chat box. It could handle images, audio, maybe data sets, and it's got to allow for things like revisions and checking citations. Then you have integrations, which connects the AI to all the other tools a person uses. For our scientists, this is huge. The app could automatically send its summaries directly into their citation manager, fitting perfectly into how they already work. And there you have it, the whole shebang, the complete AI stack from top to bottom. It all starts with the application the user sees, which is powered by that clever orchestration layer. That layer draws on up-to-date data to inform the core reasoning model, and all of that runs on powerful hardware infrastructure. See how each layer builds on the one below it? It's a beautiful thing. So, why does all of this matter so much? Well, because every single choice you make at every single one of these layers has real-world consequences. The decisions you make about hardware, models, data, and design, they will directly impact your final solution's quality, its speed, its cost, and even its safety. Understanding the stack gives us this incredibly powerful framework for thinking about and creating AI systems that are reliable, that are effective, and that are truly useful. It really transforms AI from some kind of magic black box into a set of practical, understandable choices. And that leaves us with one final and, I think, very exciting question. Now that we know how to build, what should we build next?